Empty space shouldn't exist. I know that sounds like the opening of a bad sci-fi film, but I genuinely mean it. According to quantum physics, the most precisely tested theory in human history, the vacuum isn't empty. It isn't quiet. It isn't still. It's boiling. It's churning with enough energy to tear the entire fabric of reality apart before a single atom could form. And yet, here we are. Stars are burning. Galaxies are spinning. You're watching this. The universe is, against all reasonable expectation, intact, so physicists ran the numbers. They used our best framework, quantum field theory, the same theory that gave us transistors, lasers, and MRI machines. They asked, how much energy does empty space actually contain? The answer came back, 10 to the 112 ergs per cubic centimeter, a 1 followed by 112 zeros. For every sugar cube-sized volume of what looks like nothing, when astronomers actually measured the vacuum energy of the universe, it was smaller, by a factor of 10 to the power of 120. That's not a rounding error. That's the single worst prediction in the history of science. And today, we're going to find out exactly why physics broke, and what it means that the universe survived anyway. Let me show you what empty actually means. When you picture a perfect vacuum, outer space, the gap between galaxies, you probably imagine nothing, cold, dark, still, the absence of things. Quantum mechanics says that picture is completely, fundamentally wrong. At scales far smaller than an atom, Planck-length scales, space is not still. It's a chaotic foam. Particles are constantly winking into existence, borrowing a tiny amount of energy from nowhere and vanishing again before the universe even notices they were there. The Heisenberg uncertainty principle allows this. It literally permits reality to fluctuate, briefly, as long as the books balance. Think of it like a cosmic credit card. The particles swipe. They spend a tiny bit of energy. They exist, for 1/septillionth of a second, give or take. And then they pay it back, vanish and leave no trace. Sounds harmless, right? Until you realize this isn't happening with a few particles, somewhere exotic once in a while. It's happening everywhere, in every cubic centimeter of what looks like empty space. With every possible type of particle, simultaneously, constantly, without stopping, physicists call the resulting energy the zero-point energy, the baseline hum of the quantum field, the minimum energy the vacuum can hold, even at absolute zero temperature. And when you calculate it using our most trusted mathematics, you don't get a gentle background hum, you get a scream, and that's where everything breaks. Back in the 1920s and 30s, physicists were building quantum field theory, arguably the most successful scientific framework humans have ever created. It predicted the existence of antimatter before we detected it. It explained the electromagnetic force at a level of precision unmatched in all of science. The same theory is ultimately responsible for the device you're using to watch this right now. So naturally, they turned it on the vacuum. They asked a simple question: what is the lowest possible energy state of empty space? The answer intuitively should be zero. The ground state, the baseline. Nothing happening, nothing stored, nothing lurking. That's what we wanted. That's what we needed for the universe to make sense. But the math said otherwise. Every quantum field, the electron field, the photon field, the quark field, has a baseline vibration. Think of a guitar string. You can press it against the fret, dampen it, do everything you can to silence it, and it still vibrates, microscopically, below what you can hear. The laws of quantum mechanics forbid true stillness, and you can calculate that baseline energy. The formula is elegant. 0-point energy equals 1/2 times h bar times the frequency. Simple harmonic oscillators. Beautiful physics. Right up until you try to add them all up, here's the problem. There are an infinite number of possible frequencies, an infinite number of quantum fields. You can't just sum infinities. That breaks mathematics entirely. So physicists made a practical decision, set a cutoff. The highest energy scale at which their equations could still claim to be valid, they chose the Planck scale, 10 to the 19 Geiger electron volts. The energy at which quantum gravity effects become significant, and our current physics runs out of road. A reasonable principled cutoff. They plugged that number in. They ran the integral. They waited for the result. The vacuum energy density came out to roughly 10 to the power of 112 ergs per cubic centimeter. Let me try to make that number mean something. That's more energy packed into a sugar cube-sized volume of empty space than every nuclear weapon ever built could release, combined by a factor that exceeds the number of atoms in the observable universe. If that number were real, if the vacuum actually contained that energy, space itself would expand so violently that matter could never clump together. No gravity would hold, no stars would ignite, no planets would form, no chemistry, no time for anything at all. Reality would shred itself before the first hydrogen atom could exist. That's what the math says. But here's the thing. The universe didn't shred itself. Instead of tearing apart, it expanded steadily and then, beginning around 5 billion years ago, with a slight but measurable acceleration. In 1998, two independent teams of astronomers were tracking Type Ia supernovae, stellar explosions so consistent in their brightness that they function as cosmic rulers, letting astronomers measure precise distances across billions of light years. Both teams noticed something they hadn't expected, something they actually tried to explain away at first because it seemed so strange. Distant galaxies weren't just moving away from us, they were accelerating. Something was pushing the expansion of space faster over time, not slower. Gravity, which should have been gradually pulling everything back together, was losing. Something was winning against gravity on a cosmic scale. They called it dark energy. And the simplest candidate, the one that fell naturally out of Einstein's equations, was vacuum energy itself, the cosmological constant, a built-in pressure woven into the very fabric of space, so cosmologists measured it, not with particle colliders, but with the universe itself as their instrument. They mapped the cosmic microwave background with the Planck satellite. They tracked how galaxy clusters grew over billions of years. They watched hundreds of supernovae fade across cosmic distances, and the answer came back at quiet, almost embarrassingly quiet. The measured vacuum energy is roughly 10 to the negative 8 ergs per cubic centimeter. A decimal point followed by 7 zeros, followed by a 1. Compared to the quantum prediction of 10 to the 112, do the division, 120 orders of magnitude. Let me try an analogy, and I want you to tell me in the comments if it even helps, because, honestly, I'm not sure any analogy captures this adequately. Imagine I predicted your height, and instead of getting something between 150 and 200 centimeters, I got a number larger than the diameter of the observable universe. In centimeters, that's roughly the scale of this error. In physics, when a theory is off by a factor of 2, you check your arithmetic. When it's off by 10, you revisit your assumptions. When it's off by 10 to the 120th, you have a crisis. So what actually went wrong? Here's the uncomfortable, honest answer. We're trying to force two languages that don't speak to each other to have a conversation about the same thing. Quantum mechanics governs the very small, particles, fields, probability waves, the physics of your phone's processor. It is staggeringly accurate. It predicts the magnetic moment of the electron to 12 decimal places. That's like measuring the distance from London to New York to within the width of a single human hair. General relativity governs the very large, gravity, space-time curvature, black holes, the expansion of the universe. Also staggeringly accurate. It predicted gravitational waves a full century before we could measure them, but put them together to calculate the energy of the vacuum, something that is simultaneously a quantum phenomenon and a gravitational one, and they tear each other apart. General relativity says space is smooth, curved geometry shaped by energy and mass. Quantum mechanics says space is fundamentally grainy, probabilistic, jittering with fluctuations at every scale. There is no agreed-upon mathematical framework that combines them cleanly. When you try, the equations blow up, and that's why this isn't just an embarrassing footnote. It's a signpost, a blinking neon-lit arrow pointing straight at the limits of human understanding. Every revolution in physics has started exactly here, with a number that refused to behave. Mercury's orbit didn't match Newton's equations. That discrepancy led to general relativity. The ultraviolet catastrophe showed that classical physics predicted infinite energy from a hot object. That crisis gave birth to quantum mechanics. The vacuum catastrophe might be this century's version of that moment. The crack in the wall that leads to quantum gravity, a unified theory of everything, or something we haven't even named yet. Pause with me for a second. The fact that empty space almost destroyed the universe, but didn't, that isn't a failure. That's the most important clue in physics, so how do we fix it? 3 serious proposals, each with something to recommend them and something that keeps physicists awake at night. First, supersymmetry. The idea that every particle in the Standard Model has a heavier superpartner with opposite quantum properties. If these twins exist, their vacuum energies would cancel each other out with extraordinary precision. Mathematically elegant, physically compelling. The problem: the Large Hadron Collider has searched a significant portion of the relevant mass range and found 0 superpartners. Not one. Either they're hiding at energies we haven't reached yet, or supersymmetry, as theorists imagined it, may be wrong. Second, the anthropic principle and the multiverse. Perhaps our universe is one bubble in an enormous, possibly infinite, landscape of universes. In most of them, the vacuum energy is enormous, and they rip apart before stars can form. We live in this one precisely because its vacuum energy happens to be small enough for galaxies, planets, chemistry, and life. It's not a calculation. It's a selection filter. We couldn't be asking the question from anywhere else. Some physicists love this. Others consider it barely scientific, because if every possible universe exists, you can explain anything by saying, we're in the one where it works. It's technically consistent, and technically unsatisfying. Third, we're missing something we don't have a name for yet. Maybe quantum gravity, whatever that turns out to be, reveals a hidden cancellation mechanism so precise it makes atomic clocks look approximate. Maybe the vacuum energy isn't constant at all. Maybe it's a field slowly evolving, and what we're measuring is just its value right now. At this specific moment in cosmic history, right now, tonight. As you watch this, the Euclid satellite, the dark energy spectroscopic instrument, and the James Webb Space Telescope are mapping the universe's expansion across billions of years, trying to determine whether dark energy is truly constant or quietly evolving. The data is coming, in carefully, slowly, with the kind of precision that takes years to build and seconds to overturn a theory we might not solve this in our lifetimes. And that's okay, because science isn't about having all the answers. It's about building better questions, and then building the instruments patient enough to answer them. So here's where we stand. The vacuum should be destroying everything. It doesn't. We don't know why. And I think sitting with that, really sitting with it, not rushing past it, is one of the more honest things you can do as someone who cares about understanding the universe. Not knowing isn't failure. It's an address. The universe is hiding its deepest rules in the quietest places, in the space between stars, in the hum of empty nothing, in the number that's 120 zeros wrong, and we are, slowly, patiently, with extraordinary instruments and extraordinary care, beginning to listen. What's your explanation? Supersymmetry, the elegant cancellation we haven't found yet? The anthropic filter, we're just in the lucky bubble. Or something we haven't named, something sitting in someone's head right now that would make the whole thing click. Drop it in the comments. I read every single one. And the most interesting answer gets pinned, not the most confident one. The most interesting one. And if you thought empty space was strange, wait until we talk about time. Why does it only move forward? We all experience it. We all feel it drag and fly. But quantum mechanics doesn't require it. The equations of physics work just as well in reverse. So why can't you unbreak a glass? Why can't you remember tomorrow? That's the arrow of time problem. And it's stranger than anything we've covered so far. That video drops next week. Subscribe. Turn on notifications. Because the universe doesn't give up its secrets easily, but we're getting closer. Every day,